So here's a quick recap of caches. What data is held in the cache, recently used data using temporal locality, and nearby data, spatial locality. How is data found? Well, the set is determined by the address of the data supplied by the processor, and then the word within the block is also determined by the address. In associative caches, data could be in one of several ways. What data is replaced? The least recently used way in a set is replaced. So here's a graph showing miss rate trends. So you can see the cache size on the bottom. It's increasing to the right. And then we have our, so this is in kilobytes, increasing to the right. And then we have our miss rate type and overall miss rate going up. So you can see miss rates, some typical miss rates of caches. This is 10% miss rate, is relatively high miss rate for a cache. And then this is going down to a 1% miss rate down in here, or below 1%. So as the cache size is smaller, you can see that as we increase the number of ways, we're going to get rid of our conflict misses. Okay, and so conflict misses are shown up here in those different colors. And so if you have a one-way or direct map cache, we're going to have conflicts, but as we increase to a two-way cache, we're going to get fewer conflict misses for a given size. For example, say an 8 kilobyte cache. You can see that by going from one-way to two-way, and then 4 to 8-way helps us a little bit. 4-way helps us, gives us a little bit of decrease in our miss rate, but going to 8-way did not. So did not reduce the number of conflict misses. But you can see these capacity misses down here. As we get our cache size to be larger, those capacity misses go down. And then compulsory misses, you can barely see it because they're, a very small number of percentage of the miss rate. So bigger caches reduce capacity misses, and greater associativity reduces our conflict misses. And here's some miss rate trends with block size. So again, for spatial locality, so increasing our block size from 16 bytes to 64 bytes to 256 bytes. You can see that increasing, and then we'll see what the miss rate does. And this is showing for different cache sizes. So 4 kilobyte cache up to a 256 kilobyte cache. So for smaller cache sizes, for example, let's look at this 4 kilobyte cache. You can see that increasing the block size helps somewhat. It reduces our miss rate, and a tiny bit more as we increase it to 64 bytes, but it actually goes up after we increase it even further. And what's happening is we're making the block size so big that we're actually increasing our conflict misses because of that. But for these larger cache sizes, 64 kilobytes and 256 kilobytes, we can see a decrease in miss rate with our spatial locality, but not much of a benefit after 64 kilobyte block size. So multi-level caches, we can have a level 1 cache, the one that we've been talking about, but we can also have multiple levels. Level 2 and level 3 caches are, level 2 caches are very common, and level 3 caches are not uncommon in today's systems. So the lower level caches, or the larger caches, are going to have lower miss rates, but longer access times. So we don't want to make the first level cache very large because we don't want to make it too large, in fact larger, so that we don't want to make it so large that it takes longer than one processor clock cycle to access it. So in order to get an effectively larger cache size, we increase the number of levels. So level 1 is going to be small and fast, typical size is 16 kilobytes, one processor clock cycle to access. Level 2 is going to be larger, 256 kilobytes, but takes several processor clock cycles to access. And then level 3 will be even larger with even a longer time to access. Here's a picture of the Pentium III Die, so you can see what it looks like. There's the processor is basically all the kind of random type memory or logic that you see, but then you can see the regularity of the level 1 caches, and you can see there the regularity of those memory arrays and the level 2 cache, both of which were on chip.